Ooh, wah! Okay, so we are looking at conservation of momentum. This is Unit 7, practice problem 20.7. And in this problem, we have a 6 kilogram ball. We'll call it ball A or ball 1, whatever you want to call it. And a 5 kilogram ball, ball B or ball 2. And they're moving directly towards each other in a head-on collision. And we need to make sure that, because they're moving towards each other, they're moving in two different directions. One's going like to the left, one's going to the right. That'll be something to be careful about. But after they collide, they move in opposite directions away from the site of the collision. So they kind of bounce and then go back. Once again, directions are important. Ball A has a velocity of 4.1 meters per second before and negative 1.1 after, so there's the negative. Ball B has a velocity of negative 2.9 before and something after, and we're looking for what is ball B's velocity after the collision. So the way this looks is we'll draw two pictures just like Grandpappy Botzer always taught us to do. So let's draw our initial picture first. Ball A, which has a mass of 6 kilograms, it's moving, we'll just call right positive, with a velocity of 4.1. And then ball B, mass of 5 kilograms, moving in the opposite direction, so we'll call it left here, at a velocity of negative, because it's moving to the left, or in the opposite direction, which we've defined left is negative, like that. If we draw a second picture here for our final setup, the spheres, the balls, they bounce off each other. So this one moves back with a final velocity of the A ball of negative 1.1, and the final velocity of ball B is equal to something, and we don't know what it is. We know that we are conserving momentum here, so we want to use that giant conservation of momentum equation, which reads as the mass of the first object, or we'll call it A in this case, multiplied by the initial velocity of A, so that's the initial momentum of A, plus the mass of B times the initial velocity of B equals, and then all the finals. So the mass of A, final velocity of A, plus mass of B, final velocity of B. So that's our big conservation of momentum equation. It looks very large, but when we actually break it down, we know the masses of A, we know the masses of B, we know the initial velocity of A, we know the initial velocity of B, and we know the final velocity of A. So we actually know pretty much every number here except the one we're looking for. And since we have one equation with one unknown variable, we can solve this out. It's just a matter of plugging in everything and then using that calculator and kind of churning through to find our answer. So if we dig down and we find our calculator, let's start putting in some numbers and get some values here. So mass of A was 6 kilograms times that initial A velocity of 4.1. And I always love to write everything out just to make sure I have it all. And if you're doing this at like a higher level, maybe a collegiate level, writing everything out like this could get you, partial credit later on in your life. So it's very nice to do that. Here's our negative 1.1 meters per second because it's going the other direction. And then plus, and here's the 5 kilograms from that mass. And then here's VF of B. That's what we're looking for right there. Okay, so we've got all these numbers here. Let's just start churning them together and working this down. So 6 times 4.1, that should be about 24.6. It is. And these all, because they're all momentums, are going to have units of Newton seconds. So if you wanted to keep that in mind. 5 times negative 2.9, so we're adding a negative 14.5 Newton seconds. Or if you just wanted to write that as a subtraction, you could. This is going to equal to 6 times negative 1.1 is negative 6.6 Newton seconds. And then plus 5 final velocity of B. So at this point, let's just combine more stuff together. Let's do the 24.6 minus 14.5. That's going to give us 10.1 Newton seconds equals negative 6.6 Newton seconds plus 5 VFB. And you see here, I am still rewriting everything. I'm bringing everything down just because I don't want to miss anything, right? I don't want to make a silly math mistake and just be like, oh, why did I get the problem wrong? let's just make sure we have it all right. So we add the 6.6, waching, add the 6.6, 10.1 plus 6.6 is 16.7 Newton seconds equals 5 VFB. And now we're like at the home stretch. We divide each side by the 5 kilograms, wipe, divide by the 5 kilograms. 16.7 divided by 5 is 3.34. So we find here that our final velocity for B is equal to 3.34 in units of velocity that we've been using our meters per second. And this value does make sense. It's a positive value, and that works out well for us because, you know, whenever we started with the second object, it was moving to the left, which was negative, but now it's moving to the right, which we know to be the positive direction as we defined it in the problem. So we got a positive number here. We got 3.34, which is a change in velocity from what we had previously. You know, we were going negative and now we're going positive. So that's what we're seeing here in this problem. And it was pretty much just, we drew a picture. It doesn't have to be pretty, but it has to tell us what's going on. And then we just wrote out the big green equation, that big momentum equation, and then just shoved in values. So if you can do that and then work through that algebra there, which I know you've done a million times before, we got our final answer and we're finished here. Okay, so those are some nice, straightforward, one-dimensional conservation momentum problems. That one is finished. Check out the 20.2 problem with the snowballs colliding together if you've got a snow day out there. And in some of our future videos, we'll be looking at two-dimensional problems, which get a little bit more complicated. But until then, adios, and take it easy.